Okay, so tonight we're going to talk about scatter plots. Scatter plots are similar to line graphs in that each graph uses the horizontal x-axis and the vertical y-axis to plot data points. So these up here are examples of scatter plots. Scatter plots are most often used to show correlations or relationships in data. So if we're going to compare like overall grade to time in hours, how study time affects your grades, so we want to make some kind of mathematical way of comparing these two quantities here. A scatter plot does always have to be comparing two quantities. They have to both be represented by a number. So you can't compare, students' age and the color of their eyes because eyes wouldn't be a quantity. Here's some vocabulary that you need to know. A scatter plot shows a relationship between two sets of data. A correlation, the relationship between the two variables. A line of best fit is a line that best represents the data on a scatter plot. And we're going to talk a little bit more about that in a minute. A correlation coefficient, and that is represented by an R. There just is a number that kind of helps you see what kind of a relationship or how strong of a relationship something has. Something might be very strongly correlated and some things might not be. They might be what we would say weakly correlated, and sometimes things aren't related at all, like your shoe size and the number of siblings you have. Both of those are quantities, but they don't have anything at all to do with each other, so they don't have any correlation. So that might have like a zero correlation coefficient. And from that, you'll be able to tell whether it's a positive correlation, a negative correlation, or no correlation. The correlation coefficient is between -1 and 1, so you won't ever have anything that's bigger than that. And the closer to 1, the stronger it is positive, and the closer to -1, the stronger it is negative. Here are some examples of what that might look like. So you can see that our data points are really, really close together here. It has the same line, but this is a stronger correlation than this is because the data is much tighter around the line. This one has no correlation, and this is a negative correlation, both of these. This one is weak and this one is strong, again, because your data points are tight around the line. So we're going to make a scatter plot here using this data. We're going to compare the height and the weight of soccer players. So the points on the scatter plot are, and here they are in a graph form and in point form. So we're just going to grab a dot and we're going to plot it on here. When you make your scatter plots, of course, you want to make sure that you number your axes as well as label them, height and weight, and need a title. And this one doesn't have a title on it, but it's the soccer team, so we could just label it soccer team. So height of 63 and a weight of 125 pounds is about right there. A height of, or a weight of 67, height of 156, got there. Height of 69, weight of 135. Height of 135, weight of 68, about there. And a height of 62 and a weight of 120. So these points don't make a perfect line, but what we're going to do is take a line and draw it as best we can through our points. Now, we aren't going to hit every point, but we do want to have a perfectly straight line. So you don't want to play connect the dots here. Sometimes your line will go through some data points, and sometimes it won't. It just kind of depends on the data, and it's quite all right if it doesn't. But I could put this like right here in the middle of these 2 points, but since there's 2 over here, I can kind of think about it like a tug of war. If I have this, I got 2 people over here pulling on it this direction and only 1 that way. So it's going to kind of pull my line a little bit farther down that way. I can still kind of go through there, but see how this is going to be just a little closer than that. So when you draw your line of best fit through your data, that's kind of how you decide. You want to get it in the middle of the data the best you can, but if you've got a little more on one side, it's going to kind of pull it towards that way a little bit more. So that would be our scatter plot and our line of best fit. It's just plotting points on the line or on the graph and drawing the best line you can. If you have a ruler, that's the best way to do this, is to lay a ruler down and kind of wiggle it around, kind of like I did this line, so that you get a line. Now, let's talk a little bit more about some of these correlations. A correlation can be predicted without having to observe the data in the table or graph. So this one right here, it has a positive correlation, and I know it's positive because it's going uphill. It has a positive slope. We talked about that correlation coefficient. It's not the same as the slope. It considers some other pieces of data, and we're not actually going to talk about how to calculate the correlation coefficient. You just kind of need to know that if it's positive, you have a positive correlation. If it's negative, you have a negative correlation. So this slope is positive, so I know it has a positive correlation. Now, what if I have, let's see, pick a picture. Your grade point average and the number of A's you receive. So what you want to think about is you have two pieces of data here. You have your grade point average and the number of A's you receive, right? One of them is the independent variable and one is the dependent variable. And we've talked about this before with domain and range and x's and y's and all of that. So remember, independent means the one that changes, and dependent is the one that it's dependent on the other one. It's the best way to say it. So the number of A's I receive is going to be my independent variable. I can receive 1A or 2 A's or 3 A's, but how many A's I receive will affect my grade point average. So that makes this my dependent variable. Independent, dependent. Now, a correlation, if both values go up, so if my independent value goes up and then that also causes my dependent value to go up, then I have a positive correlation. Whoops. A positive correlation. If I have my independent variable goes up and my dependent variable goes down, that is a negative correlation. If my independent variable goes down and my dependent variable goes down, that is also a positive correlation. It's whether or not they're moving in the same direction that matters. So if they both go up or they both go down, it's positive. But if one goes up and one goes down, then it's negative. So if the independent goes down and the dependent goes up, that's also negative. So your grade point average and the number of A's. So as the number of A's goes up, what happens to your grade point average? Well, it also goes up. So this would be a positive correlation. The time spent studying and the grade on your test. So which one is the independent? Well, the time is the independent, because however much time I choose to spend is independent. Now your grade then depends on the time you spend. So the more time you spend, or as the time goes up, theoretically your grade would go up. So this also has a positive correlation. Okay. All right, let's pick another one. The size of a car or truck and the number of miles per gallon of gas it can travel. So the size of your car or truck is going to be your independent variable. And then the number of miles per gallon is our dependent variable. So as the car gets bigger, so if we think about like a little car, like a little Prius, and then maybe you move up to a Honda, and then you move up to a little S10, and then up to maybe a big Explorer or big truck. So that's what they mean by the size of the car. So what happens to the number of miles per gallon as your car gets bigger? Well, it gets less. A little bitty car is going to get better gas mileage than a big one. So as my independent variable goes up, my dependent variable goes down. That means that this has a negative correlation. And one of these pictures takes me back. There we go. Okay. The number of telephones using the same cell phone number and the number of calls you receive. So the number of telephones is going to be my independent, however many phones I have using the same cell phone number. Well, that's kind of weird that you would have different cell phones using the same number, but okay. and the number of calls you receive. So calls is going to be my dependent. So if I have one cell phone that has the same number, does it matter if this cell phone has the same number? Is that going to make my number of calls increase? I don't think so. Kind of like a house phone. You know, if somebody calls your house and you have one phone hooked up to the wall, or you've got 6, if you get a call, it's still the same number of calls. So this isn't really related to itself, to each other at all. This is none. There's no correlation. They don't affect each other at all. Okay. The weight and height of each member on a soccer team. Well, this one's a little bit harder to figure out which one is independent and which one is dependent. I guess we'll say height is our independent because you do tend to kind of grow, right? So as you get taller, what happens to your weight? Well, it probably gets bigger. I mean, if you're 5 foot tall compared to somebody who's 6 foot tall, they probably weigh more than you do. This is going to be a pretty weak correlation, though, because if you think about it, you could have somebody that's exactly the same height that weighs very different amounts. But it does have a bit of a positive correlation because you would kind of just think of the taller you get, the more you weigh. But it's pretty weak. Okay. And the size of a person and the number of fingers he has. Okay, so size of the person will be our independent. So as your size gets bigger, number of fingers is our dependent. Well, that doesn't change, does it? The number of fingers you have are just the same no matter how big you are. So this one has no correlation at all. Okay. And that is it.